Okay, well, there's some finite dimensional space in which this talk is about as far from the other one as you can get. So this rock is from the southern Nevada, eastern Mojave. I'm going to make an argument that there are places in the West, in the deserts, which can be thought of as somewhat analogous to the eastern U.S., and talk about that. Now, okay, this probably, by the way, the projector squeezes it, stretches it out horizontally. This is actually more precarious looking on the graph here than it is in there, but it's pretty precarious looking. Okay, now the thing that makes this useful for things like sigma is we have an idea of age dates here. This is Dylan Rood from Lawrence Livermore Laboratory, who's pointing to a spot where the cosmogenic age date is 20,000 years, 20 Ka. Just behind him is a big rock, which was standing up on top of there and which was toppled by some vandal sometime after we actually went out and tested the acceleration that would topple it over and so forth. So we have, this is about 16 kilometers from the San Andreas Fault. If those ages are right, then we're talking like 100 magnitude 8 earthquakes this has been exposed to. But I don't think we can say that. But certainly dozens of large earthquakes on the San Andreas have occurred and left that rock standing there. So that now we have a large sample in time, and we've already had people discussing here, how do we get at this parameter for multiple earthquakes on the same path? A lot of these would have the same magnitude and same distance from the San Andreas Fault. So I think this really potentially gets at the question of sigma directly. Here's one from Pennsylvania in the eastern U.S. And so you might say, well, why don't you just go out to the eastern U.S. and look for all of these and answer all your questions here? You don't have to worry about all this theory. Well, one of the problems is in the eastern U.S., the erosion rate is much faster than it is in the southwest desert. I don't know how old this rock is, but you probably couldn't argue that it's more than like 1,000 years and so forth. But I still think it's worth, this is courtesy of Ken Hudnut, who's been looking for such rocks in the eastern U.S. So preliminary, we're going to have a workshop on October 4th and 5th in Reno, sponsored by the National Earthquake Hazard Reduction Program, which is focused on how do you put precarious rocks information into hazard maps. And of course, one of the things is not going to be just the median and mean, but it's going to be the standard deviation sigma. This is a list of the group of people who worked in this. Most of these people have been supported in part by the Southern California Earthquake Center and focusing on the mechanical aspects, the age, and the geomorphic situation where these rocks occur from. So we have a couple of thousand rocks like this in Southern California now at various places, and I think we can start to say something pretty important about seismic hazard. Now, near the end of the talk, I want to discuss the idea of using parts of California or the Southwest as analogs for the eastern U.S. And the way I'm going to argue is that the attenuation for this magnitude 6.8 earthquake, which occurred down in Baja California, is compared on the right with the intensity curve, intensity for the magnitude 7.2 1940 earthquake. Now that intensity map is typical of what you get earthquakes along the major fault zones. This is typical of what you get on the left in the Baja Peninsula, where there's low heat flow, very uniform crust, no deformation, and I think geophysically you can argue it's a good analog for the eastern U.S. And I'll talk a bit more about that at the end. Just quickly, if you plot that intensity map on the Atkinson-Boer curve that came out just, I guess it was 2006 or 2006, for a 6.8, it falls right on. It's halfway between the 7.5 and the 6.5. So the attenuation is very, very similar. In other words, you have huge ground motions at large distances compared to what you get in the western U.S. Then I'm going to end and speculate on the epistemic uncertainty about what happens at closer distance based on some data. So that's to whet your appetite for the end of this talk. Okay, this slide here shows locations of various clusters of precarious rocks in Southern California. There's a couple of thousand of them here. The ones that I've got marked with little symbols here are areas where there's an important test of the recent hazard maps. And a basic conclusion right off the bat is all the 10% and 50-year hazard maps are totally consistent with the precarious rocks. That is, the more frequent earthquakes and the 500-year repeat time are all consistent with precarious rocks. The other extreme is the 1% in 50 years are all inconsistent. And that tells you right away, hey, there's something funny going on here that you go from very low probability events being inconsistent to high probability events being consistent. In between, the 2% and 50-year map is given here. That's in between. And the red ones are all the sites that are inconsistent with the 2% and 50 years maps for some reason. So I'm going to discuss a couple of those sites where sigma, I think, is the primary reason for the discrepancy. Let me see if there's anything else. Yeah, well, I should say where the two areas are. I'm going to consider the area here. This is Lovejoy Buttes, which is 17 kilometers from the San Andreas Fault, and it's had repeated magnitude 8 earthquakes here, so we got a good sample to investigate sigma. And the other place is halfway between the Elsinore-San Jacinto Fault. Magnitude 7 earthquakes are occurring here roughly every 1 to 200 years. And so at any given site along here, these rocks here that I'm going to show you have been exposed to many, many earthquakes also, of roughly, the bigger ones about the same magnitude. Now, going to the San Andreas site at Lovejoy Buttes, which is about 15 kilometers from the San Andreas Fault, the deaggregation shows that almost all the hazard comes from those big earthquakes on the San Andreas Fault, as you would expect. They're repeating every 1 to 200 years with huge magnitudes and a distance of 15 kilometers. So essentially all the hazard comes from these. That makes it an ideal place to test the sigma for these large earthquakes. And this is the map, a figure that I published in 1999 with John Anderson showing the results of this, except I've added quite a bit to the graph. First of all, instead of having just like 10, now we've got 30 rocks in this region at Lovejoy Buttes here, and we have quite a few, like 20 rocks out here at large distances, and otherwise this graph is the same as I published back there. And you can see that it's consistent with the 10% and 50-year hazard map. It's consistent with the median the values of ground motion as indicated in the graph up here. And it also happens to be consistent with the Sterling and Wisnowski, which was the first hazard map that was ever published for Southern California, similar to the ones we customarily look at. Now, he used only characteristic earthquakes, no small earthquakes, just every section of the fault had the characteristic earthquake on it, and he didn't use any sigma whatsoever. So he just took the mean value, median value, mean value, and used it. And of course, their predicted ground motion is very low because you don't have any sigma in there at all. Now, if you jump up to the 2% and 50-year map curves up here, of course, the predicted ground motion goes way up. And if you went to 1%, it'd even go higher. So these rocks, which apparently have been subjected to dozens of large magnitude earthquakes on the San Andreas Fault, certainly are not consistent with this 2% and 50-year. Now, it could be that the median or mean is lower, or it could be that sigma is lower. I mean, is too high. But we should. The fact that it's been exposed to so many earthquakes indicates, I think, that there's something funny about sigma. Okay. Now, the second place I want to discuss where sigma makes a huge difference is, as I said before, this place between the San Jacinto Fault and the Elsinore Fault. You find these precariously balanced rocks along a line more or less halfway between the two. You don't find them very close to either fault. And obviously the reason for that is the ground motion away from those two active faults, which have had many magnitude 7 earthquakes according to the current USERF model for California. They've had lots of magnitude 7 earthquakes occurring during the lifetime of these rocks. So again, we can get a test about sigma. And this is a modification of the graph we showed in our geology paper showing the data that we had then, which is in the big black dots, and various curves where you get about the same answer, namely that the median or mean curve, they're pretty close, and some of the hazard curves are pretty close too. If you add the 1 sigma deviation from the Abramson and Silva, it moves it up here. And then I've plotted the 2% and 50-year maps and the 1% up there at the top. So one of the complications we have here is that if you want to compare with the hazard map as distinct from the attenuation curves, well, just to be sure you understand, since this is one fault here and the other fault here, of course, the attenuation curves die off in both directions. And so the rocks over here got knocked over by this fault, and the ones over here got knocked over by this fault. The ones in the middle are left. The thing that I've added here is a series of open circles for various fragilities of rocks. And these are place sites and numbers that we've determined since the previous paper was published by testing in the field and doing more accurate measurements. And you saw the list of names before. Rasul Anushapur is in the audience here, and he's been one of the prime people that's been working on determining the toppling accelerations for these rocks that we have here. There's about 50 of them along that line that we can get that constraint on. So, the complication I mentioned is that the hazard maps, of course, include random background earthquakes, for which there's no geologic information or geophysical information that there's any faults around that line in the middle where it could generate those earthquakes. But the hazard maps smooth the data out so that there's lots of ground motion caused by earthquakes that probably aren't real. But I asked Art Frankel if he would take those out of the 2% map, and it drops it down here, but still they're inconsistent with most of the precarious rocks at the low probabilities, like 2% 50 year or 1% 50 year, but they're more or less consistent with the median and the 10%. So again, my first reaction is, it sounds to me that it's sigma that's doing this, but we can debate that. I'll just show you some picture of the rocks between here and, along that line, so you get a feel for what we're talking about. Some of these you can go over, well, a vandal pushed one of those over I was telling you about. We want to get these all measured before vandals head out there and start pushing them over too much. This is my granddaughter and I underneath one of these, which we've tested this one by a curious accident. We don't want to destroy data, obviously. We'll let the vandals do that. But the developer is building a bunch of houses, and he said, we're going to tip this one over anyway because it's too dangerous. And we said, oh my gosh, let us go out there and accurately measure the force and everything and we did this, and so we got the tipping acceleration for this one, which was one of the points I plotted on on the graph. This is one of the prettier ones. And this is an example of Matt Purvance and Rasul out testing the quasi-static toppling accelerations for these, which typically when we go to a dynamic model on the shake table, or we've tested a lot of these on the shake table, and we had an article in the Journal of Structural Engineering showing the results of a large number of tests of similar rocks on the shake table. We put a force through more or less the center of mass of these things, and then calculate the quasi-static, and then make a correction for the dynamic toppling acceleration. John Anderson just sent me this map and this figure. I think Norm has already mentioned a number of studies showing that if you use this path sigma instead of the total sigma and reduce it, John is working in Japan on sabbatical, and he's doing a lot of this data with the Japanese. And of course, you reduce the hazard out at low probabilities and high ground motions quite a bit by changing the epistemic uncertainty. Okay, just to indicate what might be some of the epistemic uncertainty problems you're dealing with in the eastern U.S., I want to consider this Baja magnitude 6.8 earthquake. I haven't heard anybody say they have a 6.8 earthquake in the eastern U.S. Where you have ground motion on it. So I'm going to argue that it might be a good analog for certain aspects of the eastern U.S. The earthquake was down here in Baja, on this fault here, and there were no strong motion recordings, so we don't know what the near source accelerations are, but the intensity map was plotted for California, where there was quite a bit of, there were a few observations, which I'll show you the spectra of if we have time here. And here again is this remarkable thing that the, where's my, oh, here it is. The intensity contours for this are way out compared to what happens in this very active zone of the Imperial Valley and the San Jacinto Elsinore faults down here, where you'd expect attenuation to be quite high, and here it's very, very low, just like you might expect for a stable region. I actually have done geophysical refraction studies down Baja California. The heat flow is low. The structure is very similar to the eastern U.S. There's very little sediment, and so that's why I'm arguing that it could be an analog. If you plot the intensity data and a few strong motion records, it fits out here just where you'd expect for the eastern U.S. This is the Boer and Atkinson-Boer recent paper showing the dark lines for the eastern U.S. Attenuation curve, which Dave can explain all the details that went into that. All I want to say is out here at the U.S., a long ways north of the earthquake, the ground motion is very consistent with what you'd expect for the eastern U.S. for a 6.8 earthquake. So you might say, okay, well, that's interesting. Maybe we can use it. And by the way, there's a lot of earthquakes down there, small and large. So you can do a lot of the same kind of stuff that we've talked about here in this talk using that data. The path between the source of these earthquakes in the U.S. is nice and homogeneous, but there is an active fault down there. I shouldn't say active. It's very inactive and just luckily had an earthquake on it. It hasn't moved more than 1 kilometer in the last couple of million years. So it's very, very, very slow, inactive fault, but it did have an earthquake for us. Okay, now, here's the real surprise. If you go into the epicentral region of that earthquake, what do you find? You find these incredible balanced rocks in the distance range 1 to 5 kilometers. Well, actually, 100 meters to 5 kilometers from that earthquake. And I think you might say you're kind of surprised. I was surprised. And anyway, these are very precarious. There's a thesis you can get from the CITRIS and Ensenada a master's student went down there and modeled these rocks and also modeled the various ranges of ground shaking that would take them to knock them over to get a constraint on the PGA, and compared it with various curves here, which I won't go to in detail, but depending on whether you plot it along the axis of the rupture, we know exactly where the rupture is in this case. That's another good thing, is this as an analog. And if you take the values that she got, and I think I agree with, they're way down here, whereas the Atkinson-Boer numbers here, which are based on simulations, right, Dave?
Yes.
Primarily on simulations, they're way down here, would knock those rocks over. So this is really a drastic difference. And I think, at least from a scientific point of view, I would like to understand how this can be. So do we really want to put an attenuation curve like this in here for a stable continental region, which I think you can argue this is a stable continental region. Whether it's equivalent to the eastern U.S., I don't know. Now, some people would say, well, how do you know that it was actually really it wasn't down at depth or something? Well, in this case, we have a complete map of the whole rupture length of the fault. We know the stress drop is normal, about 30 bars, and this is just an example of the offset that occurred at the surface. So it's a typical earthquake. There's nothing funny about it, except the ground motion is extremely low right in the source region. So how can that be? There seems to be there's a contradiction between the intensity being high in the U.S. and the ground motion being low. Well, obviously the difference has to be in the frequency content. The intensity at large distances is primarily about 1 hertz, if you look at the records that arrived up there. So I think this is what it says, is that you can't infer the high frequency content of an earthquake just by the intensity at large distances. As in the case of the eastern U.S., we have many examples of very large intensities at large distances, but we don't have very many examples of what the actual ground motion was in the near field. This shows you the length of the rupture, which was very well outlined after the earthquake. People went out and measured the offset. But this slide also illustrates that this is a very homogeneous granitic batholith, similar to many places in the eastern U.S. There are some very thin alluvial deposits here, but none of these are more than probably less than 100 meters, probably all of them just a few tens of meters at most in thickness. By the way, the rocks are consistent with the few adobe buildings that were in that area. They were essentially just stacks of rock and mud, and some of them were knocked over by this earthquake. In fact, the people who did the intensity map couldn't believe it, so they just ignored it. But the intensities were extremely low in the epicentral region based on the few adobe buildings that were standing. Here's the record from San Diego and also El Centro. Of course, El Centro is a station that's out on sediments, but either way, you can see that the predominant frequency out here is down low at like 1 second. It knocked a lot of stuff off of shelves in Jacumba, in north of the border, quite a few places. So it wasn't trivial shaking north of the border. Here's a spectrum of that event, but one other question then remains. How do you know what the attenuation is at high frequencies if you don't have any data other than the rocks? This seems to suggest, on the one hand, the attenuation is very low for 1 second energy, right? But what do you know about high frequencies? Well, fortunately, we have recorded earthquakes from this same area many, many times. And the answer is high frequencies propagate like crazy compared to the rest of California. This is a typical California earthquake record in California from earthquakes at the same distance in the active tectonic areas. And you can see all the high frequencies are gone. This is from an earthquake in the same area as the earthquake I've been talking about. So it's clear that the attenuation going from this earthquake to north of the border is extremely low. It propagates high frequencies extremely well. It propagates low frequencies extremely well. And so that's the end. I want to say that this, you can conclude this as an epistemic problem or an aleatory problem.
Thank you very much. Okay, questions for Jim? Gabe. Okay. Yeah.
Two questions, Jim. First one, in terms of the precarious rocks that you showed earlier, is it possible to reconcile them by simply using the non-ergodic assumption? In other words, saying, well, yeah, that rock experienced 10 earthquakes, but it was really one earthquake that happened identically 10 times? Or do you need a lower sigma?
No, they're fairly close to,
Okay,
if you make sigma 0.
No, my point is, what if you make sigma typical value, 0.5, 0.6,
Yeah.
but assume one earthquake? Well, assume, again,
Well, they're consistent
one
with
occurrence.
One earthquake. The most probable realization of one earthquake is the median, and that agrees with the rock.
Okay, well, yeah, but you might go more, because I think that may be that's one possible solution. Again, just simply with a non-ergodic assumption, but the same sigma.
So we've had like 25 earthquakes occur here.
But it's really one.
Well, I proposed that in that paper I wrote.
Yeah, exactly.
If you remember.
Yeah, you were the one who suggested non-ergodic.
But I only proposed that as a thought experiment. I don't believe that that sigma is 0.
Well, no, it's not that sigma is 0. It's that you have one realization of that sigma.
Well, no, there are many realizations. There's at least 20.
No, but it's one. Of the ground motion, of the residual, yeah. One realization of the residual. Even though there were many earthquakes, they are the same earthquake, the same identical earthquake.
And same ground motion.
And the same ground motion happening several times.
Yeah.
In which case, on average, you have or on median-wise, you have the median, and you might go a little bit into the tail.
Yeah.
So that's one possibility. Again, sigma may be right, but is highly ergodic because of the path effects and so on. Okay, that was my first question.
Well, yeah, it depends on how you define sigma.
Yeah. But again, we're moving in that direction, towards the non-ergodic representation.
Yeah, if you go to non-ergodic
Yeah.
all the way, then I think I showed all those sites in Southern California, most of them become in agreement with the precarious rocks if you do that.
Okay, yeah, all right. The other question is down to the Baja. You mentioned normal mechanism.
No, it's the strike-slip fault.
It's a strike-slip fault.
It's pure strike-slip
Oh,
fault.
but you mentioned normal. You used the word normal.
Well, I
normal
meant,
in the sense of
I meant it's
regular.
an ordinary earthquake.
Ordinary, okay.
Ordinary.
All right, that makes it
Yeah,
clear.
you caught me as a geophysicist in my own terminology.
Not
I'm an engineer.
abnormal.
I'm
Yeah,
an
it's not
engineer.
abnormal. Yeah. What that brings up a question, though. I was talking with Dave. Most of the Atkinson-Bohr data is from thrust faults. We know that thrust faults have high ground motion. And when I gave this talk back at the Eastern section a few months ago, and so one of the questions is, are there any strike-slip faults in the eastern U.S.? And the answer is, there was a paper given showing that, in fact, there are strike-slip earthquakes at various places in the Appalachians, and maybe one of the earthquakes in the 1812 sequence was a strike-slip earthquake. The others were different. Oh, is it 2 strike-slip? Okay, 1 thrust.
Okay, Paul.
Could you show us the geological map that had the fault rupture on it, please?
Yeah.
I'd like to see where the epicenter is and where the rocks were, because maybe directivity can explain some of this.
No, keep going. Keep going. It's quite a bit ahead.
I'm thinking that if the rocks are near the epicenter, then they don't see directivity, but Southern California would. Yeah,
there you go. Okay. Yeah, that's a good question, and unfortunately, it makes things even slightly more puzzling. Of course, we didn't have any local seismograph stations down there, so the epicenter is somewhat uncertain. But all the locations that people did from the California data indicate that the epicenter was up to the northwest, which would imply that the rupture went to the southeast. But I have those graphs, I can go into them. The most precarious rocks are down here to the southeast, which I'm almost ready to argue that they're probably wrong in their epicenter location because, you got the problem. But they've located a number of other earthquakes, including some where I have independent information and some where I went down with students and actually located the aftershocks. And it's hard to believe that they could have made that big of an error and that the epicenter was really here when they say it's here. So I don't know for sure about that. Okay, what was the rest of the question?
That's it.
That's it?
All right. More question for Jim? Yes? Oh, Julian.
Jim, when you're using this kind of observational data to compare with probabilistic estimates, isn't the only valid way that you could do it is you say, let's say you said there's a 10% probability, you find the ground motion which has a 10% probability of exceedance in a given period of time, and did more than 10% or less than 10% of the potentially precarious rocks get toppled in that period of time. In fact, you need several of those periods of time to fully do it. But you're only looking at we know that from simulations and measurements that the variability over very short distances of the ground motion in any given earthquake is enormous. And you're looking at the ones which have survived, either because we're overestimating the motions and the hazard, or because they're just the survivors. Unless you also, I don't know how you can do this, identify the ones that did get toppled and look at them in proportion. It's like when people take individual recordings and compare them to probabilistic hazard maps. It's almost, it's a questionable comparison in that sense.
Well, okay, to answer your question, we've checked that. And it's geologically completely impossible that would occur. And I'll give you the argument. If you look at the Purvance et al. Paper that was just published with Norm as a author on it, not that I'm going to give him credit for any of this particular part.
He's sometimes not aware that he's on these papers.
But it's easy to check the statistics on that. If what you had said had been true, then it would apply there were many more. So instead of 50 rocks at Lovejoy Buttes, there would be actually thousands. And there's nowhere on Earth that kind of density of rocks has ever occurred. So that's one thing. And if you look at the jointing and you compare with areas like, I had a point on the map where you're way out in eastern California where there's no earthquakes. And we're using that as a blank. And what's the distribution of rocks in an area where you don't have any shaking? And the answer is it's almost completely independent of the aspect ratio. In other words, you have the same number of rocks that would be toppled by 0.4, 0.3, 0.2. When you get to 0.1 G, you're way out. Of course, you're very, very fragile rocks, and you're out there. And they're actually at Granite Pediment, which is way out there. You have a lot of 0.1 G rocks. I mean, they're real easy to tip over. But there's less of those than you would expect for a flat distribution. Now, so I think the argument geologically, geophysically, is that the distribution of aspect ratios that forms normally is more or less flat. If you buy that, then you go to the 0.3 G ones, and then you calculate how many 0.4 G ones, because now they're less fragile, right? And you're exposing them to the same ground motion. You would like to have 10,000 more rocks at 0.4 G than you do at 0.3. And it's just absolutely not observed. What you observe is that in areas where there's no earthquakes, the distribution as a function of toppling acceleration is essentially flat. As you get closer and closer to the San Andreas Fault, you knock off the higher frequency the more fragile ones. So I think that disproves that theory.
Thank you.
Great. Thank you very much, Jim. Appreciate that.
Okay.
Now,